Welcome to my talk. My name is Michaelas. I'm a PhD candidate at Paderborn University in Germany, and I will talk about the work by my three colleagues and me on a submatrix-based method for approximate matrix function evaluation in the quantum chemistry code CP2K. What we're doing with CP2K is so-called ab initio molecular dynamics. So we simulate the motion of atoms at a finite temperature. But instead of relying on some models for the forces, we actually compute the forces as the gradient of the total energy of the system. And these energies we can compute from first principles using electronic structure methods, in particular density functional theory, or short DFT. The problem here is this works really well for small molecules like the one shown on the top here. But the computational effort rises cubically with the number of atoms. So if you want to simulate maybe 100,000 or millions of atoms, this quickly gets out of hand. One important data structure we're working on is the so-called Hamilton matrix H. So this is the matrix representation of the energy operator. And the cubic scaling of the matrix operations we have to do on this matrix is just not practical for large-scale simulated systems. But if we use atom-centered basis functions to represent the orbitals, we will see that this Hamilton matrix actually becomes sparse. So while the dimension of the matrix still grows with the number of atoms, the number of non-zero elements only grows linearly with the number of atoms as well. And by exploiting this sparsity, we can actually construct linear scaling methods for DFT. As I already said, we use CP2K. So this is an open source quantum chemistry code that implements lots of methods and also linear scaling DFT. In particular, it implements the density matrix-based DFT. The approach here is that we compute the so-called density matrix D directly from the Hamilton matrix H with this sign operation here. And from the density matrix, we can then determine the energy that we were interested in. So overall, this then looks like this. We start with the Hamilton matrix H. With this sign function, we get to the density matrix D. From that, we can determine the energy, and from that, we get the forces for our simulation. So what is this sign function? If we think about the sign function for a scalar value, we can denote it as x divided by the absolute value of x, so that we get either +1 or -1, depending on whether the value was positive or negative. And if we reformulate this a bit, like here, we can actually directly apply this to matrices as well. And what this is doing then is that it maps the eigenvalues of the matrix towards +1 or -1, while leaving the eigenvectors of the matrix unchanged. And the sign function can be computed iteratively. So this is done in CP2K, for example, using the so-called Newton-Schulz iteration, which is shown here. So we just start with the matrix, and in each iteration steps we have to perform a couple of matrix multiplications, and ultimately this will converge against sign of A. So we already see that the computational kernel here now becomes matrix multiplication. One important part of CP2K is the libdbcsr library, which is actually used to do the multiplications. So remember, we have now a sparse Hamilton matrix. And in CP2K, this is represented as a block sparse matrix. So the matrix is divided into relatively small blocks, maybe 5 to 30 rows and columns per block. And then the sparsity pattern is only utilized on top of these blocks. The blocks themselves are stored in a dense format. And these blocks typically correspond to, either molecule or parts of a molecule. And the responsibility for these blocks is then distributed among all MPI rings. So we can see here a quick example. The darker areas should denote blocks with non-zero values, while the white areas are entirely zero. And then maybe rank 0 just knows about these 4 blocks, rank 1 knows these 9 blocks, and so on. And on top of that, each rank knows which other rank is responsible for which block. The multiplication itself is then performed using a modified Cannon algorithm. So what we actually have to do is multiply lots of these small blocks and do regular communication with our neighboring MPI ranks. So now towards our work. Our goal was to extend this method to better exploit the ever-growing floating point performance we have in current HPC systems, and also to ease the integration of accelerator hardware such as GPUs and FPGAs. Our idea here was to utilize some approximation, while of course keeping the introduced errors low such that the results are still usable. And our idea here is to utilize the so-called Submatrix method. This method we proposed 2 years ago as a highly parallel method to approximately compute inverse p-th roots of matrices. But we will see that this can also be applied to the sign function. And the rough idea of this method is that we disassemble our sparse n times n matrix into n smaller, nearly dense submatrices, and then apply the function of interest, so here the sign function, to all of these submatrices. And then we can construct an approximate solution for the original matrix from all these partial solutions. And the benefits here are, well, firstly, it's embarrassingly parallel because all the n computations of the sign functions can basically be done in parallel. And also we have to compute the sign function on dense instead of sparse matrices, which might be a lot easier. Okay, so quickly to explain the submatrix method, we start again with some kind of sparse matrix, and again the dark areas should denote non-zero elements, while the white areas are 0 elements. And now we go column by column, so we look at the first column here and determine which blocks are non-zero and which are 0. And then we basically remove all the columns and rows where we have a 0 element in the first column. And this leaves us with this 4x4 values here, which we then can extract into a separate matrix, which is the first submatrix. Then we perform our function of interest here and use the first column, so the one that corresponded to the inducing column here, as a result for the approximate end result. And we do the same, of course, for the second column. We see here that we get a slightly bigger submatrix in this case. Then we continue this for all the n columns. So we have seen that the size of the submatrix is determined by the number of non-zero values in a column. And this is interesting in our case because we have seen that the number of non-zero elements in the Hamilton matrix only grows linearly with the number of atoms. And this means that the number of non-zero elements per column roughly stays constant. And with that also the size of the submatrices stays constant. So the only thing that rises is the number of submatrices that we actually need to process. So overall we get a linear scaling with the number of atoms, independent of the scaling of the function we are interested in. And here's a quick maybe proof that this is actually the case. So here we looked at systems of various size filled with water, and we see that for an increasing number of water molecules the dimension of the Hamilton matrix increases linearly, but the size of the submatrices is actually limited, and from a certain point it doesn't grow any further. Okay, now on to how we implemented this method in CP2K. There were a couple of challenges. One is that the matrix is stored in this dbcsr format and it's actually block sparse. But turns out that we can apply this method on the top of blocks instead of single elements. So this works very analogously to the first example. We look now at the first block column here, extract all the blocks into a submatrix, and the submatrix will generate the result for the first block column again. Another more difficult challenge is that the matrix is stored in a distributed fashion. So if we take this as an example, so we want to create the first submatrix from these blocks, and maybe say rank 0 is responsible to do so, we have a slight problem here because all that rank 0 knows is this partial view on the matrix. So what we did is we introduced an initialization phase, and as a very first step we generate a global view on the sparsity pattern. So each rank looks onto its own blocks, which are 0 and which are non-zero, and then this information is shared such that every rank knows about the sparsity pattern. As a second step, we actually transfer the required blocks. So taking the example from before, rank 0 needs these blocks from rank 1 and these blocks from rank 2, so they are transferred to rank 0. Then there's the main computing phase where, in this case, rank 0 can construct its first submatrix, process it, and basically generate the first result column. And then in the end, we need a finalization phase where we communicate back the result blocks to the ranks that are actually supposed to have them according to the DBCSR format. I've shown these phases now for a single submatrix, just an example. In reality, we do the initialization phase once, so the sparsity pattern is only exchanged once, and there are no duplicate block transfers in the initialization. And the computing phase covers all submatrices such that these operations can be parallelized. Okay, one question is, how do you process the submatrices? And in general, you can use the very same method that you originally used on the overall matrix. So in this case, this would be this iterative Newton-Schulz approach to compute the sign function. We found that for these dense matrices, it's often quicker to do an explicit eigendecomposition. So what we can also do is to decompose A into its eigenvectors and eigenvalues, and then apply the sign functions to all the eigenvalues of the matrix, and use these modified eigenvalues and eigenvectors to generate sign of A, where A is the submatrix in this case. In our paper, we actually describe many more details on our implementation. So there are questions like, can you combine submatrices to minimize the computational effort? How do you assign submatrices to ranks to balance load and also to minimize the required block transfers? And we exploit our explicit eigendecomposition to apply the method to canonical ensembles. So if you're interested in these details, I can recommend reading our paper. Now I want to quickly share our results. So we evaluated our method on the Noctua compute cluster at the Paderborn Center for Parallel Computing, where each node has basically two of these Xeon Skylake CPUs, 20 cores each. So we have 40 cores per node. And as a data set, we chose a cube containing liquid water, and we used a single zeta valence basis set, which is basically a minimal basis set with one basis function per hydrogen atom, 4 functions per oxygen, such that each of these water molecules will generate a 6x6 block in our Hamilton matrix. So first of all, I want to share the quality of results, because the Submatrix method is, of course, an additional approximation. And one important parameter here in CP2K is the epsilon filter argument, which keeps the matrices sparse by basically setting all the values that are below this epsilon filter to 0. And of course, the quality of results heavily relies on this argument. So what we see here is the absolute error per atom depending on the epsilon filter. And we see it in orange for the conventional Newton-Schultz approach and in blue for our submatrix method. And what we see here is that it overall behaves very similarly. So there's not a big additional error introduced here by the submatrix method. Then on to performance. The submatrix method fundamentally requires sparse matrices because otherwise your submatrices get very big. So we see this when we have a very small epsilon filter here, that the submatrix method just takes much longer. But we see that this drops off, and round about 10 to the minus 5 as epsilon filter, there's a crossover point where the submatrix method starts to perform really well and also better than the original Newton-Schultz approach. We also confirmed the linear scaling behavior, so scaling the number of atoms here on computation on 2 nodes, and we see that the compute time rises strictly linear. We evaluated strong scaling, going from 40 to 320 CPU cores, and in this case we compare against a theoretically perfect scaling, and we stay above 83% efficiency during this entire scaling experiment. We also looked at weak scaling, going from 40 cores to 1280 cores, while scaling the system from 12,000 atoms to 384,000 atoms. And what we would like to see here is basically a flat line. And what we see is that the submatrix method gives us a slightly flatter curve than the conventional Newton-Schultz approach. Lastly, I want to briefly touch hardware acceleration, because we now don't have distributed block sparse matrices anymore, but instead operate on locally stored, nearly dense matrices in the size of a couple of thousand maybe. And these are best conditions for offloading to dedicated hardware. And if we use iterative schemes, all we need to implement is basically matrix multiplication. So one experiment we did was on NVIDIA Turing GPUs, where we used cubeless to implement a third order iterative scheme and managed to achieve 33 to 100% of the theoretical peak performance of our hardware, depending on which data type we used. So we see that for half precision it wasn't as easy to get to the peak performance as, for example, for single precision. We also looked at FPGA acceleration and offloaded the matrix multiplication to an Intel Stratix 10 FPGA, where we used the reference design by Intel, but we enhanced it to use multiple kernels to increase the performance and to partly overlap computations and communication with the host. And in theory, our design would be able to achieve 3.4 teraflops, but for the observed submatrix sizes, this drops down to 2.7 teraflops. In the end, we were able to get 1.8 teraflops for the entire sine iteration. The difference here is mainly caused by communication overhead, so we are currently working on moving the entire iteration scheme onto the FPGA. In summary, we have shown a new linear scaling method for DFT in CP2K utilizing the submatrix method. This allows us to transform the distributed matrix operations into computations on local dense matrices. And we have shown that the new method is basically as precise as the conventional Newton-Schultz approach, while showing a favorable strong and weak scaling. Especially, it's well suited for the integration of hardware acceleration into CP2K. Finally, I want to thank the DFG and the Competence Center HPC NRW for funding our work, and the PC Square for providing us compute time and FPGA advice. And with that, I conclude my talk. Thank you for listening.